had to find out whether engineers designing turbines are using this ancient knowledge for more modern applications.
A strange spiral sits in the water, spinning slowly like a piece of ancient machinery. But this isn't some historical curiosity. When engineers first ran simulations on this design, they thought their computers had malfunctioned. The numbers showed power output that seemed impossible, especially in water that was barely moving. Then they built a real prototype in Poole Harbor, England. The results matched the predictions almost perfectly.
My attention was caught by Liam F1, made by a Dutch company, with its revolutionary design making this wind turbine supposedly highly efficient and super cheap to run.
What they discovered was something nature had been using for millions of years, hidden inside a principle that's over 20,300 years old. So what makes this spiral so special? The ancient genius behind the spiral. Archimedes lived in a world where moving water uphill was brutal, exhausting work. Every drop required filling buckets, lifting them, carrying them without spilling, then emptying them and starting over. Irrigating fields, draining mines, keeping ships afloat during leaks, all of it demanded chains of workers performing the same backbreaking sequence over and over. Around 250 BCE, Archimedes changed everything. His screw concentrated all those separate steps into one continuous motion. A helical blade wrapped around a wooden shaft, sealed with pitch and angled into the water. Turn it, and water climbed upward inside the spiral channels, defying gravity with nothing more than steady rotation. No lifting, no carrying, just spin. The Greek historian Diodorus wrote about how rapidly this invention spread. From the Nile Delta to what's now Spain, everywhere Archimedes traveled, communities immediately adopted his screw. It wasn't just better than the old method. It made the old method obsolete overnight. For over 2 millennia, these screws have pumped water across the Mediterranean and beyond, and many are still in use today. But Archimedes understood his invention only as a mechanical device working against gravity. He saw it as a way to lift water, or reversed, as a way to capture energy from falling water. He never realized there was something else hidden in that spiral shape, something far more powerful. How the Archimedes screw actually works. The mechanics are surprisingly straightforward. The helical blade creates pockets that trap water. As the screw rotates, these pockets move along the spiral path. Because the screw sits at an angle, each rotation pushes the water a little higher. The water doesn't flow continuously. Instead, it's captured in discrete volumes that march upward with each turn. The original application relied purely on gravitational force. Whether you were pumping water up or generating rotation from water falling down, everything depended on vertical movement. The force acted perpendicular to the spiral surface, straight down toward Earth's center. This principle still powers some modern installations, like the screw turbine at Munich's Isar River, which generates electricity from the downstream flow of water influenced by gravity's pull. But that's only half the story. Buried in the geometry of the spiral is a completely different mechanism, one that has nothing to do with gravity and everything to do with lateral fluid dynamics. Archimedes never saw it. The mathematics to understand it didn't exist yet, and for thousands of years, nobody else saw it either. Nature's blueprint, the eel's secret. Eels and moray eels move through water with remarkable efficiency using what biologists call anguilliform undulation. Their bodies form a traveling wave, a sinusoidal curve that ripples from head to tail. This isn't random wiggling. It's precisely coordinated propulsion. The key detail is that the wave travels backward along the body faster than the eel moves forward through the water. This speed differential means the eel's body accelerates water backward, generating forward thrust through Newton's third law. Push water one way, move yourself the other way. The entire motion happens in essentially 2 dimensions, like watching from above as the eel traces a smooth sine wave through the water. Now here's where it gets interesting. If you take that 2-dimensional sine wave and wrap it around a cylinder, you create a 3-dimensional helix, the exact same curve. The mathematical relationship between an eel's swimming pattern and an Archimedean spiral isn't just similar. They're geometrically identical, just expressed in different dimensional spaces. An eel has to flex its entire body to create that wave pattern. It's muscularly expensive and requires a flexible skeleton. but a rigid spiral already has the wave shape permanently built in. Rotation around the central axis reproduces the exact same relative motion that the eel achieves through body deformation. The spiral doesn't need to flex. The geometry handles it automatically. This means a rotating spiral can interact with flowing water the same way an eel does, creating or capturing thrust along the axis of rotation. It's not just pumping against gravity anymore. It's functioning as a propulsion device, and it works in both directions. Spin it to push water, or let water flow past it to generate spin. This bidirectional capability is what makes spiral turbines fundamentally different from Archimedes' original gravity-dependent design. The hidden power of rotation. When you rotate a spiral in water, each section of the blade moves through the fluid at a specific angle and velocity. The helical shape means different parts of the blade interact with the water differently, but they all contribute to the same overall thrust vector along the axis. It's coordinated propulsion without requiring any coordinated flexibility. The same principle works in reverse. Place a stationary spiral in flowing water, and the force of the current pushes against those angled surfaces. Because of the helical geometry, these forces don't just push the spiral downstream. They create a torque around the central axis, causing rotation. Attach a generator to that rotating shaft, and you're converting the kinetic energy of flowing water directly into electrical energy. This isn't theoretical. It's been tested and measured. The question is whether it's better than conventional propeller designs, which have dominated marine engineering for over a century. And in several important ways, the answer appears to be yes. Where spirals beat propellers. Propellers are efficient when water flows straight into them, perpendicular to the blade disc. Change that angle, and efficiency drops fast. The effective surface area decreases with the cosine of the angle, and turbulence increases. Propellers are optimized for straight-on flow, and they suffer when conditions vary from that ideal. Spirals behave differently. When water hits a spiral turbine at an angle, something counterintuitive happens. Yes, the force vector becomes less aligned with the axis of rotation, but simultaneously, the effective surface area that the flow encounters increases. More of the spiral's length is exposed to the current. In many cases, these two effects balance out, and the turbine maintains its power output even when flow isn't perfectly aligned. Sometimes performance actually improves at slight angles. This makes spiral turbines far more resilient to real-world conditions. Rivers don't flow in perfectly straight lines. Tides create complex shifting current patterns. Turbulence is constant. Propellers struggle in these environments. Spirals handle them naturally. Then there's rotation speed. Propeller turbines spin fast, often exceeding 100 rotations per minute, sometimes much more depending on the design. Spiral turbines rotate slowly, typically under 20 RPM for comparable power output. This is a massive advantage for wildlife safety. A fast-spinning propeller is a blender. Fish, marine mammals, and other aquatic life can be injured or killed by contact with the blades. A slow-moving spiral is gentle by comparison. Even direct contact rarely causes harm. The large, gradual curves give animals time to sense the structure and move away, and even if they touch it, the low speed minimizes injury. For tidal and river installations in protected waters or areas with significant marine biodiversity, this could be the difference between a project being approved or rejected by environmental regulators. There's also the matter of cavitation. High-speed propellers can create low-pressure zones where water vaporizes, forming bubbles that then collapse violently. This cavitation damages blades and reduces efficiency. Slower rotation speeds in spiral turbines significantly reduce this problem, potentially extending operational lifespan and reducing maintenance costs. The historical disadvantage. So if spiral turbines have all these advantages, why haven't they replaced propellers already? The answer comes down to manufacturing costs and perceived efficiency limits. Propellers are simple to produce. A few blades attached to a hub, cast or machined from standard materials. Mass production drove costs down decades ago. Spiral turbines are geometrically complex. Creating a true helical shape with precise curves requires more sophisticated fabrication. Historically, this meant higher costs per unit, especially at smaller scales, and for most of the 20th century, engineers believed spiral designs couldn't match the peak efficiency of optimized propellers. Propeller turbines have reached what's called the Betz limit, the theoretical maximum efficiency for extracting energy from a moving fluid, which is about 59.3%. Get close to that, and there's not much room for improvement. The assumption was that spiral turbines would always fall short of this benchmark, making them a niche solution at best, suitable only for specific applications where their other advantages outweighed the efficiency penalty. That assumption held until someone decided to test whether it was actually true. Spiralis Energy's breakthrough. A company called Spiralis Energy approached the problem differently. Instead of accepting conventional wisdom, they used computational fluid dynamics to simulate thousands of spiral variations, tweaking parameters to find configurations that maximized energy capture. Their models suggested that with the right geometry, spiral turbines could compete directly with propellers, matching or even exceeding their efficiency in real-world variable conditions. Simulation is one thing, hardware is another, so they built a prototype, 6 meters long, and deployed it in Poole Harbor on England's southern coast. Before testing, their simulations predicted the turbine would generate 2.59 kilowatts under specific flow conditions. The actual measured output was 2.5 kilowatts. Even accounting for friction losses in the test rig, which weren't part of the simulation, the deviation between prediction and reality was only 1.5%. That level of accuracy is remarkable. It validated not just the turbine design, but the entire simulation methodology. With that confidence established, Spiralis Energy can now rapidly iterate designs. They don't need to build and test every variation. They can simulate performance for different sizes, different water speeds, different installation environments, and identify the optimal configuration before committing to manufacturing. This dramatically accelerates development and reduces costs. Their production strategy relies on 3D printing, which eliminates many of the traditional manufacturing challenges. Complex geometries that would be expensive or impossible to cast or machine can be printed layer by layer. Customization becomes trivial. A turbine optimized for a fast, shallow river can be printed just as easily as one designed for slow tidal currents in a deep channel. The company projects costs between 5.8 and 11.6 cents per kilowatt hour, competitive with conventional tidal turbines and cheaper than many renewable energy sources. They're planning to scale up, with turbines ranging from 5 kilowatts for small installations to 500 kilowatts for industrial-scale power generation. Their next prototype will be 6 times larger than the Poole Harbor unit, intended for full deployment as an operational power plant. What comes next? Prototypes are always promising. The real test is longevity. Can these turbines operate continuously for years without significant degradation? How often do they need maintenance? What are the repair costs when components fail? These questions don't have answers yet. Spiralis Energy needs long-term deployment data to prove durability. Investors will want to see performance metrics over multiple years, covering different seasons and varying environmental conditions. Material fatigue, biofouling, corrosion in saltwater, all of these factors will affect operational lifespan and total cost of ownership. But the early signs are encouraging. The wildlife safety profile addresses one of the biggest regulatory hurdles for marine energy projects. The resilience to variable flow conditions means installations can be placed in locations where propeller turbines would struggle. And the manufacturing approach allows for rapid scaling without massive capital investment in specialized production facilities. If the durability testing goes well and the larger prototype performs as predicted, spiral turbines could become a standard component of renewable energy infrastructure within the next decade. Rivers, tidal estuaries, even ocean currents could be harnessed with minimal environmental impact, generating consistent baseload power without the intermittency problems of wind and solar. It's a strange thought. A design principle older than the Roman Empire, combined with computational tools that didn't exist 5 years ago, might be one of the keys to a sustainable energy future. Sometimes the best innovations aren't entirely new. They're old ideas finally understood correctly.